Hopefully that will work, or it won't. These are the two possibilities. Oh, good, we're up. Okay. So, now that we know we're up, we'll get going. So today we're going to talk about isotopes and what that means. So, before we get too much into it, I am going to go up to my version. Again, as always, if you go into your OneNote, if you prefer to work digitally, there's a digital copy there waiting for you. But presumably most of you will work on paper. And just like yesterday, just like every day, when I'm done teaching this, by the way, I will distribute the filled out copy to you, so you always kind of have that in your back pocket to look at should you need it. Now let's get going. Oh, good, it's blank. Am I like not connected to the Wi-Fi or something? Hello? There we go. Okay. So, let's talk. Recall the periodic table. Here we have an entry on the periodic table. What element am I looking at here?
Lithium.
Lithium. Very good. What can you tell me about lithium just by looking at this?
It has 3 atoms. Its atomic number is 3.
Good. Its atomic number is 3. And what does that tell me? Yep.
There should be 3 protons.
Okay, so a neutral lithium atom will have 3 protons. What else can you tell me based on that?
3 electrons.
3 electrons. Good. Again, it can gain or lose electrons. It would then become an ion, but a neutral lithium atom is going to have 3 protons and 3 electrons. There's always as many positive charges as negative charges in a neutral atom. What is this 6.941, and what's it telling me?
The atomic mass.
Very good. This is what we call the mass number, the average atomic mass. In this case, it's roughly 7. What can I determine from that? What can I determine from that? What will that tell me about an average lithium atom?
The number of neutrons is 4.
Okay, and how did you know that?
Because its atomic mass, the trapped atomic number is the 5 neutrons.
Cool, and why is that? Why does that matter? Like, why do I subtract that? So, like, I've given you the secret, the code to the universe. Like, take that number and subtract that number, and it tells you how many neutrons. That's cool. Why does that work? Why must there be 4 neutrons if this thing has 3 protons but a mass of 7?
Because protons and neutrons weigh the same.
Good, they're the heavy stuff.
Roughly the same.
Yeah, they both weigh roughly 1 atomic mass unit. They're the heavy bits. Whereas electrons are the
Way lighter ones?
way lighter. That's right. So when you gain or lose an electron, your mass doesn't change appreciably. It would be the equivalent of saying, if you cut my arm off and put me on a scale, will my weight change?
Yes.
Yeah, right? That would be noticeable. My arm presumably weighs something. If you pull one of my hairs out and I step onto the scale, am I going to see a change? Not appreciably, right? Does that make sense? That's kind of the difference we're talking about here. When it comes to mass, you can basically ignore electrons. Questions about that? No. Good. Okay, we'll move on. So here's my question. Why isn't that 7 or greater? Why isn't that 7 or greater?
Because sometimes lithium atoms might have a different number of neutrons.
Oh.
It's just that on average you'll get 6.941. It's like I can't have 0.3 of a child.
But you can.
Bingo. The mass number is an average. The mass number is an average. Lithium doesn't always have 4 neutrons. And I'm just going to quickly remind myself what, because I cheat. I want you guys to know, like, I practice this stuff. I don't just throw this together. I I rehearse. You might not be able to tell because of the gross incompetence, but like, this is me trying. So lithium doesn't always have 4 neutrons. In fact, there's kind of 2 different versions of lithium that are stable and that exist. Sometimes we find what we call lithium-7, which is the one you would expect. And lithium-7 has, what particles go in the nucleus again? Yep, and how many protons does lithium have? Remind me? And we said lithium 7, if it has a mass of 7, how many neutrons must it have?
4.
4, good. And then how many electrons does lithium have?
3.
And how many fit in the first shell? I know we haven't talked about this yet, so if you forget, don't worry about it. How many?
2.
Yeah, 2 is correct. We can fit 2 electrons in the first shell, and then I'm going to have to put a third electron out in the second shell. So that would be what do we call this kind of diagram?
Bohr-Rutherford?
Yeah, very good. A Bohr-Rutherford. A Bohr-Rutherford. A Bohr-Rutherford. I'm just going to not say that anymore. I'm doing my best. Oh, that hurt my feeling. Okay. So that's one version of lithium we see. But if you look in nature, we sometimes also see a version that has 3 protons but only has 3 neutrons. And that can also be stable. Now, if it had 3 protons and 3 neutrons, how many electrons would it still have? Yep, still going to have 3. All right, that doesn't change it. Still needs 3 electrons to be electrically neutral. So both of these exist. What would we call this lithium?
Broken.
This one we call lithium 7. What do you suppose we would call this one?
Lithium 6.
Very good. We call this lithium 6. And based on the average mass, what is most lithium? Look at the average, look at these. Which version of lithium is the common one?
7.
Very good. Can everyone see that? How did she know that lithium 7 must be the common one? How'd she know?
The average is really close to 7.
The average is really close to 7. Can everyone see that? The average is like 6.9. So imagine that there are only 2 heights. Some people are 6 feet and some people are 7 feet. If the average height was 6.9 feet, it would mean that most people were 7 feet. Can you kind of just picture that? Right? If you put 100 people in a room, most of them are going to be 7 feet, and then there's going to be the odd person who's 6 feet. Now, I know that's not how height actually works, right? Height goes all different numbers. So we can tell just looking at this then that this is more common and this is less common. And we get that based on the average, but both of these exist. These are different, and I'm going to introduce a word. Well, I mean, we've already said the word, but these are different isotopes of the same element. So isotope is just a fancy word that means version. Iso meaning same, topic comes from, oddly, the same root as proton. They have the same number of protons, they're the same element, but they have different masses. And it is the neutrons that make the masses different. The truth is, there's actually lots of different isotopes of lithium, but there's only 2 that are stable. Does that make sense? You think about, anyone ever driven a car where one of the tires was unbalanced? What's it feel like? Feels rough, right? Car shakes and shakes. So atoms are always in motion. They're moving and they're spinning. And if the nucleus is imbalanced, if it's not stable, it'll fly apart. It'll be radioactive. So there's only some combinations of protons and neutrons that work to make a stable atom. For lithium, you can make a stable atom with 3 protons, 4 neutrons, or you can make a stable atom with 3 protons and 3 neutrons, and any other combination will fly itself apart, often quite quickly. So you can make them in the lab, like using a particle collider, but they do not last long. They are short-lived, unstable isotopes. Does that make sense? But lithium has 2 stable isotopes, 2 isotopes that can exist and do exist in nature. And there they are. There's not always only 2. There's not always only 2. Hydrogen, if we look, I don't have the periodic table up here. I got to put one right there. But I don't have the one there right now. But hydrogen, if we look on the periodic table, hydrogen has an atomic number of 1, and its mass number is 1.0079. That's right. Off the dome, 1.0079. So normal hydrogen has how many protons, how many neutrons? 794 if you want the next digit, not to get too fancy here. It has 1 proton. And normally, how many neutrons does it have? 0. And so you're going to see, I'm going to show you another way we write this sometimes. Sometimes we write it like I just did up there. We'd write it as H-1, hydrogen 1. But another way you'll see it written is with a subscript like this. Hydrogen 1 is called Protium. And I got to check if it's an E or an I. I have it written with an I. I hope that's correct. And protium has 1 proton, no neutrons, and a single electron floating around. That's called protium. If, like me, you went off the page, you should probably just highlight that and slide it up. Just like that. I find that funny every time, and I apologize if you don't.
Don't worry, I find it every time.
Why? I don't know why you're not working. Okay.
Remember that if you accidentally draw somewhere, you can just tap and delete it.
Funny every time. Okay, so that's hydrogen with no neutrons. Now, if hydrogen did have a neutron, what mass would it have? So if now it had a proton, but it also had a neutron, we'll draw it first. 1 proton, 1 neutron. How many electrons would it need now? How many electrons would it need now?
1.
Still just 1, because the electron, to make it neutral, just has to balance that proton out, right? Neutrons have no charge. Good. This would be called, this has a name, it's called deuterium. Ooh, okay. I think that's the spelling. Can somebody I don't know if the E is there actually. Can somebody check that for me quickly? That matches what I did in my notes, but I'm still nervous. If somebody can give that a quick Google for me. And while somebody's doing a quick Google for me, what's the mass of this? How much does this weigh? Yeah, good. We'd call this H2. And note, deuterium is twice as heavy as normal protium, as normal hydrogen. Twice as heavy. It's meaningfully more heavy. But even more so, you can actually get a stable isotope of hydrogen that has 2 neutrons. How many electrons would this need? Still just 1. Very good. This is actually called tritium. Tritium is extremely rare and extremely expensive because it takes a lot of purifying to produce, but it exists. Tritium. What's its mass? Very good. In nuclear reactions, tritium can be used to make hydrogen fusion happen more easily. If you're like a hydrogen bomb, like a nuclear reaction where they're trying to get fusion of hydrogen to form helium, they use tritium because it's heavier, and so it has more force of impact when it collides, and it makes nuclear collisions easier to happen. Does that make sense? So they also, in if you've ever heard of heavy water, has anyone ever heard that before?
I've heard of dry water.
Interesting. Heavy water is water where the hydrogens in the H2O are deuterium or tritium, and it literally is water that is just water. It behaves chemically like water, but it is meaningfully heavier than normal water because it's made from heavier atoms. Interesting stuff. Questions about that? Different versions of the same atom. And what do we call those different versions? Isotopes. Very good. So again, different isotopes are more or less common. Just really quickly looking at hydrogen, what's the common isotope of hydrogen? What is most hydrogen?
1.
Hydrogen 1. So how many neutrons does a typical hydrogen atom have?
1.
Careful, it has a mass of 1, which means how many neutrons? 0. Good. Don't worry about it. Easy mistake to make. Excuse me. Okay, so from there, you should be saying, well, how do we get this number in particular? Where does that number come from? How do you get the average? Because wouldn't the average of these just be 1 plus 2 plus 3, which is 6, and then you divide by how many, and 6 divided by 3 is 2. So shouldn't the average be 2? Why is the average 1.0079, not 2?
Because hydrogen 1 is like way more common than deuterium and tritium.
Good. So listen, look here. Say we did a survey of this class and I asked, how many pets do you have at home? How many pets?
2 cats.
2 cats.
2 dogs, a cat, a guinea pig, a bird.
Give me a number. That's 5?
Yeah.
5.
Dog.
1. 3. Cool. 3. Toby, what you got? How many pets at home?
None.
None. 0. Cool. 1. None.
1.
None. 6. 2.
2.
2.
2.
2. 3?
Yeah.
3.
Well, technically 4.
Do I count each fish individually? I guess I count each fish individually, right? So 6. Now, if we're going to find an average of how many people we have, right, we just add all those numbers together and then we divide by how many people in this class, right? That's easy, right? But what if it wasn't like that? What if I didn't have everyone in front of us to count? What if instead I had a table that looked like this? What if I knew that 25% of our class had no pets, 10% had 1 pet, 30% had 2 pets, 35, 65, 20% had 3 pets, 60, 85, 10% had 4 pets, and 5% had 5 pets. By the way, I know that that's not actually at all the numbers we came up with, but all the same, if I just had this chart, could I still find an average?
Yeah.
Can you still find an average if I don't actually know? Because does this tell me how many people are in the class?
Yeah. No.
Not directly, right? But how would I find an average with that information? Little math lesson. Have you done weighted averages in math before? I get to teach you math? Hey, that's exciting. Hopefully I don't screw it up. I might screw it up. Let's find out. So the way you take a weighted average is this. You take a weighted average by adding all these up, just like you normally would with an average, but if this one, look here, this one, I have to add it up not just once, but like 25 times, right? And then this one, I need to add 1, but I can't add 1 just once. I have to add 1 10 times, right? Does that make sense? And then I have to add 2 30 times, right? And I have to add 3 20 times. And then what does percentage always add up to? What am I dividing by at the end?
100.
Beautiful. Does that make sense? It's actually not that bad, right? Now, do I want to sit with my calculator and go 0 plus 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 1 plus 1 plus 1? Am I going to do that?
No.
I could. Like, I totally could. And then divide by 100 at the end, and it will work, right?
You gotta put the bracket.
But is there a quicker way to do that?
1 times 10.
And I could even do 1 times 10 plus 2 times 30 plus 3 times 20 plus 4 times 10 plus 5 times 5 divided by 100. As long as I use brackets carefully, like you said, I'll get there. Nothing wrong with that. That's cool. Is there an even quicker way? Yeah, exactly right. Instead of dividing by 100 at the end, we can divide all the percentages by 100 right to begin with. Does that make sense? In other words, we can express the percentages as a decimal. Is everyone comfortable writing a percentage as a decimal? What would 25% be if we wrote it as a decimal?
0.25.
0.25, good. What would 10% be if we wrote it as a decimal?
0.1.
0.10. What would 30% be?
0.3, etc.
Yeah, 0.2, 0.1, and then obviously that's 0.5, and there we go. I'm pretty sure it's 0.5.
0.05.
You're the teacher now? Is that how this works? Fine. No, you're right, of course. This should be 0.05. You got to watch out for that, right? If it's a single-digit number as a percentage, then it's going to have to be in the ones, like the 100ths column here. It's going to have a 0 in front of it. And if you're not sure, by the way, what could you do with that number on your calculator to make it a decimal? You could always just divide it by 100. So you don't have to be able to do that in your head. It's okay if you can't. And now, I would just do this times that, plus 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 this times that, and I'll have my average. And so let's do that. Oh boy. Okay, ready? So I could just say, I'm going to skip the zeros, because does adding 0 matter? It does not. So I could say 2 times 0.1. Oh, what am I doing? I'm sorry. Yeah, I have failed already. This should be 1 times 0.1 plus... Where's my just nice number keyboard? I just updated my computer, and yeah, I'm not traditional. Okay, well, whatever. Plus 2 times 0.3. This is not better. But okay, we'll get there. Plus 3 times 0.2. Plus 4 times 0.1. Plus 5 times 0.05. And it tells me that the average number of pets in that classroom would be 1.95. So the average student...
Cool, I've got an above average number of pets.
Now again, I just made these numbers up. But still, has 1.95 pets. Does that basic process make sense? Do we kind of understand how we got there? That the reason this works is because we're really just saying, okay, I'm going to count this 25 times out of 100. I'm going to count this 10 times. I'm going to count this 30 times. I'm going to count that 20 times. I'm going to count that 10 times. I'm going to count that 5 times. And I'm going to divide it all by 100. It's just taking an average the way we normally do, but instead of having to punch 100 things into my calculator, I can do it a bit quicker. Is that cool? Would you tell me if it wasn't?
Probably not.
Why not? Tell me, I don't mind. You can be like, hey, Orlando, you suck, and that didn't make any sense. And I mean, don't say that, because that'd be really rude. But you can say like a polite version of that, and I'll try and make it not suck. Okay. So, here we are now applying this back to isotopes. If we look back at lithium, we said lithium has how many isotopes? 2. And one of them is lithium-6, and one of them is lithium-7. By the way, if I didn't give you the exact masses, we could just use 6.0, because it will always give you a decimal place. There's a bit of a disconnect here because neutrons and protons don't weigh exactly 1 atomic mass unit, but also, and this is, ready? Look at me. I'm about to say something, and can you just trust me that's true and not think about it until you take university chemistry or university physics?
No promises.
Okay. When the bonds form, some of the mass of the protons and neutrons actually gets converted to energy, and it's no longer mass. So the mass of the subatomic particles can actually decrease, and that can be turned into energy in accordance with Einstein's statement of general relativity that energy is equals mass times the velocity of light squared. Don't worry about it. All right, look at me. Don't worry about it. You'll see that even when we're talking about lithium-6 that has exactly 3 protons and 3 neutrons, this number doesn't quite work out as beautifully as it should. If you just take the mass of a proton, the mass of a neutron, and the mass of 6 electrons and add it all together to get this, you'll be like, that doesn't quite add up. And it's because there are things that happen in the nucleus where you actually get mass becoming energy. Look at me. Don't stress about it. It's something that's going to matter like at the 3rd decimal place. Note that this is like 6.0. This is 7.0. The isotopes will basically always be this number 0.0. And then when you get to these decimal places, you're going to get some weirdness. All right, is that fair? Don't stress about it. It's not a big deal. Okay, having got that out of the way. So here are the two isotopes. Remind me, which one's the most common isotope? Lithium-7. How much more common?
A lot.
91
You have to do the math, but like comparison, it's like 92 versus 8, right? Like a real difference. Like a really, it is a lot more common. So to calculate the average atomic mass, here's what we do. And I'm going to introduce you to some nomenclature you might not know. We use M for mass. And in science and math, when we put a bar over something, that bar means average. In fact, it means mean. And do you know mean, median, and mode? You guys talked about that in math? Yeah, don't worry about it too much. In common everyday language, we mean that that's the average. And that M means we're talking about the mass. So if I want to say the average mass, the way we'd normally write that is an M with a bar over top. And then, usually in science, we throw a little subscript in there to say what I'm talking about. So when you see that symbol, let's interpret this. This is saying what is the
Mass.
average
Mass.
of lithium. Does everyone see that? That's a really logical symbol, isn't it? What's the average mass of a lithium atom? It's all right there. A lot easier than writing the average mass of a lithium atom, don't you think? Bit of practice, you'll get used to it. So the average mass of lithium, okay, ready? You might not have seen this before, but don't stress out. Has anyone seen in math before the use of a capital sigma? That's a Greek letter sigma, don't stress about it. Has anyone seen that before? Or even just seen it like on a piece of paper and been like, that looks sciencey, that looks fancy. No worries, do you know what it stands for? Well, sigma is the Greek letter S, it's the equivalent of our letter S, and it is a short notation for sum. What does it mean to take the sum of something?
I want to say it's add.
Bingo, beautiful. This tells us we're going to add a bunch of stuff together. Does that make sense? So this is the sum symbol, and it means we're going to add them up. So as soon as you see that symbol, you should know, oh, I'm going to be adding a bunch of things together. And the reason they don't just write the number of things is because in the case of lithium, how many things am I going to have to add together? 2. But if I was doing hydrogen, how many things would I have to add together? 3. When we get to this question for iron, how many things am I going to have to add together? 4. And when you do magnesium as your homework, you're going to have to do 3. Does that make sense? So the symbol sum.
Interruption.
Yeah. Yes.
Hello?
Hi.
Hi, could I please have Grace Stratichek dismissed? She has an appointment.
You bet. Yep, she's en route. So Grace, you'll be able to find the rest of this online, and if you have any trouble, just shoot me a message, okay? Cool. So this symbol just says, however many isotopes it has, the math we're about to do, you're going to do it for all the isotopes, and then what are you going to do with them all? Add them together. Does that make sense? So we're going to add together, oh, that's not black. We're going to add together the mass of each isotope times the abundance of each isotope. Just like we did for the pets. We take the number and multiply it by the percentage, and don't forget that this needs to be as a decimal. All right, that's really important. Right? It's not that important. You could just, it's important. Don't worry about it. So you want to do mass times abundance. And then, after you've done mass times abundance for each one of them, you're going to do what with each of those? Add them up. Does that make sense? Mass times abundance for each isotope, and then add them up. Do you think you can give this first one a crack? Why don't you try it? Listen, if you get it wrong, that's okay, then we'll fix it. But see if you can do that. For each of these isotopes, you're going to take the mass and you're going to multiply it by the abundance. But you're going to make sure for the abundance that you remember to use it as a decimal. And then when you've done the mass times the abundance, what are you going to do with them? Add them up. All right? Can you try that? Just give it a try. All right? And after you've tried it, we'll take it up together. I think you're going to do great. That sigma notation, or sum notation, by the way, comes up a lot in math. And as a result, it comes up fairly often in science, especially physics. You take physics, you'll see things like that quite a bit.
Thanks for the heads up.
The other way you'll sometimes see it written, if they didn't want to use the sum symbol, can I just show you this? What they would sometimes show it as is this. They'd say the average mass is equal to the first mass times the first abundance plus the second mass times the second abundance, ... all the way to the last one. Does that make sense? So they might show it to you this way, or they might show it to you that way. They both will get you the exact same place. But I think this is kind of nicer to write, to just say, isn't that nice and clean? Look how nice and clean that is. Anyway, I do not care how you write it. Write it in a way that is logical for you. But I want to keep my page clean. Okay, I'm going to give you, I don't know, 1 minute and 17 seconds more. Yeah? That's awesome. The only thing we forgot is as a decimal, which is fine. So that just means you can divide this by 100 and you'll be good. Like if you prefer to divide by 100 at the end, that's okay. That'll give you the right answer. Or you should put that in as like 0.0759 and that in as 0.9241. Does that make sense? Cool. Give it another try, but you've got the right numbers. You're good. You're doing great. Yeah. No problem. So what we can do is we're going to say one way we could do this is we could get a calculator out and we could say 6.0151 and add that together 8 times. 8 out of 100 of this. And then we could punch in plus 7 92 times, right? And then divide by 100. Does that make sense? But another way, first things first, what's that as a decimal? As a decimal, you always just divide by 100. So if you want to pull up a calculator on there, okay, just grab a calculator and you can even do it right in OneNote. If you have one, that's not. Okay, yeah. So, yeah, calculator. Oh, it lost. Just type calculator. It's a really nice computer. There you go. Yeah, so you can do 7.59 divided by 100. It'll give you his. Oh, 7.59. Yep, and then divide by 100. Awesome. Okay, so when you go to use this, you're going to use 0.0759. Awesome. And then when you go to use this percentage, what's that as a decimal? By the way, if you want to use division, you can always just press the little slash button like fraction. Yeah. No problem. And all those keyboard shortcuts. Awesome. And then when you go to use this one, you can do 0.9241. So then the way to get the average is we're going to add them up. So we're going to take the first one. And what's the first mass? Awesome. And we're going to multiply it by the, which is 0.0759. Awesome. And then we're going to add, what's the next one? Yep. Great, and what are we multiplying that by? Awesome, and that'll give you the weighted average. And weighted average means it'll give you the average taking into account that this one is really common and this one's not very common. Because again, if you just added these together and divide by 2, it'd tell you that the average is like 6.5. But that doesn't take into account that most lithium looks like this, and only a little bit looks like that. Does that make sense? Yeah. Awesome. Plug that into your calculator. You'll be good to go. Howdy. I'll be right there. I am coming. You have to do them one at a time and then add. You can't add and then multiply.
So it's multiply
Right.
each individual, then add
Multiply each
together
individual
the
one,
results.
then add together. That's right.
Gotcha.
Yeah, order of operations. I do see you there, Bria. I'm just going over here first. Yep. That looks good. But you don't then have to divide by 100. You go like that. And so you got that one, but now just do it all at once. So now that's good. Now put plus. And also careful, that should be 0%, right? 7%. That says 75%. Yeah, there you go. So now add the next one. And what number do we leave with here? Yep, keep going, right in the same line. So 7.0160. And what are we multiplying it by? Yep, and as a decimal, right? So showing that as a decimal. Yep, keep going. Give me all 4. Awesome. Does that make sense? And you can do that in one step in your calculator, right in your phone, and it'll give you the average. Does that make sense? Cool. Let's throw this together. How was that, guys? We'll take it up now. So if it stressed you out, don't stress. But did that feel okay? All right. So talk to me. First of all, I want to write the average mass of lithium. How do I write that symbolically again? How am I going to write the average mass of lithium?
A line over mass.
Yeah, a line over, do I write the word mass?
No.
Nope, just the M. Awesome. And then what?
LI.
Beautiful. All right. Now, we're going to add up the mass of each isotope times the abundance. So let's do the first isotope. And the first isotope I'm going to color as yellow. What is the mass of the first isotope?
6.0151 atomic unit.
Good. So 6.0151 atomic mass units. And what am I multiplying that by?
7.59.
7.59%. And when I go to do math with that, what should I make sure I do?
0.079.
Good. I need to use it as a decimal. Again, if you don't, you can just divide by 100 at the end, but I prefer to just plug it in as that. So when I do this as a decimal, it's going to be 0.
7.59.
Almost. We're really close. Now that would be 75%. So what do I need leading there?
0.
Yeah, that's right. Don't forget, if it's a one-digit percentage, you've got to make sure you put that leading 0 here. And if that's the only mistake you make, you're doing all right. We'll get it right. But 0.0759, that takes care of my first isotope. What's my second isotope? What's the mass of my second isotope?
7.0160.
Very good. And what's the unit on that?
92.41.
Very good. And how would I write that as a decimal?
9241.
Very good. Exactly right. And then sigma notation tells me I should do what with these two calculations? Careful. What are we doing? Adding them up. Inside these we multiply, right? But between them, we always add them up. And you don't actually need these brackets. They're not doing anything. I kind of put them there just to help us organize. If you want to put them in brackets, it's not going to hurt anything. It'll work, but you don't need them. And so now I can just, in my calculator, type that in. I can say, I really have got to figure out, it used to go to a number calculator. I got to figure out how to find that. 6.0151 times, well, that's new. I've never seen that before. I like that. Let's see if it works. 0.0759. And then we have to add 7.0160 times 0.9241. And hopefully this will give me a number. I've never used it with these multiplication symbols before. Usually on a computer you use the star, right? So it might yell at me. No, it knew! Awesome! And what do I get as my number? Now, if you used a calculator, it probably gave you a couple more decimal places than this, which would be nice. Does anyone have it with all the decimal places for me? Yeah.
6.9400.
6.9400, and I'm going to stop there. And what would the unit on this be? We did atomic mass units times no unit, and then this one's atomic mass units times no unit, so the unit should be? Oh, come on. Mass is measured in atomic mass units. This is a mass, so it's going to be? Atomic mass units. Good. And that's how we find a weighted average. And again, why isn't this average just 6.5? I added 6 to 7. Why is the average not just 6.5? Like, why do I have to go through all this nonsense? And why do I get this number that isn't in the middle of those two? Yep. That's okay. Take a look at this. Why isn't the average right in the middle of the two? I've already said, but it's easy to lose this. Forest and trees, right? Yeah.
Lithium 7 is more abundant.
Good. The reason the average isn't right in the middle is because they're not equally common. This heavy isotope, there's a lot of it. And this light isotope is relatively rare. Hello.
I apologize to
Don't apologize.
about the isotopes. It smells great in here. Somebody's wearing peppermint. I've locked myself out of my classroom. My
Oh, no.
warrior key.
You may. Do you know that I stole Britt's keys, so I'm working on the borrowed key today.
I'll be right back.
Look at us.
Thank you kindly. Sorry to interrupt you.
Yeah, so really common isotope, uncommon isotope. So the average is going to be a lot closer to the really common one than the uncommon one. Does that make sense? Cool. And that's how we get there. Questions about that calculation? All right, I'm going to have you guys try one where I don't do a whole lot of talky talk. I'm just going to sit up here. And this one's tricky because how many isotopes do we have here?
4.
Oh, what a pain in the butt. But you can do it. I have faith in you. All right, so I want you to tell me what is the average mass of an iron atom based on this table of all the stable isotopes. And be careful when you turn these into decimals. You may want to actually grab a calculator and divide them all by 100 because it's easy to mess up where you put the decimal place with that one. All right? So do your best. I have faith in you. If you need help, ask each other. If each other aren't able to help you, then ask me. All right? Yes, sir.
How many decimal points do you go to?
Sorry?
How many decimal points do you go to?
For now, eventually we're going to do a whole day on decimal places and stuff, so I don't want you to stress that too much now. As a rule of thumb right now, look at the question and just kind of match it. So right here, this question has, what, 4? So your answer should go to 4. Does that make sense?
Sure.
Eventually I'm going to have a much more strict answer to that, but for now, that's good.
Do you have peppermint in there? It's such a nice, fresh smell.
That, I don't, but I like it.
It's really
I'm
nice.
enjoying it too. Sorry. I've had this guitar squirreled away here all summer, and so I haven't played it in a while. So it's nice to see it.
I like music.
I like music too. Actually, we're better at it. So I should probably practice. We're taking weighted averages, Catherine. Yeah. Sorry? Ooh, good. That's what I get paid the big bucks for.
So you said to match, if I were to
Awesome.
match, it would just go to nothing.
Oh, are you doing these one at a time?
Yes.
Don't do them one at a time. Do it as one, because you'll go crazy. Do it as one big calculation. So exactly how I have it written on the page here, plug it right in like that. You'll be a happier camper. And guys, that's actually a good rule of thumb. As a rule, we're gonna develop the habit of don't do like every little mini calculation in your calculator as you go. Try to get in the habit of get on the page what the calculation is going to be, and then plug it into your calculator as one step. All right? Can you please turn that off? I don't actually want you, watching media whilst in my class. I find that improper, shall we say? I'll knock you out. That's where I'm really going with this. Yeah.
So,
But your setup is great. I love that. That's perfect.
I'm
But
supposed to divide these by 100, right?
yeah, and just don't lose the 8.5 there. But that's fine. So your calculator is defaulting to 2 decimal places. That's good to know. I will grab you a more robust calculator in just a moment. Oh, that should be 10028. Because yeah. Okay, so give me a sec. I'm gonna grab you one of those yellow calculators. They're nice. Does anyone else want a nice, like, just actual, like, handheld, like a calculator as opposed to like using a phone or whatever? Yeah, I'll grab just a flat of them. All right. Go on. No problem. So try punching that in. Do it all in one big step, just like you have it on the page. Who said here yet? There you go. Oh. Looks beautiful. Yeah, that looks great. I can't guarantee that the math is right because I can't do that in my head, but the setup is perfect. All right, what do you say? Should I give you guys about 3 more minutes? Does that feel like enough? Yeah, Mr. Orlando, that sounds good. Oh, good. Thanks, Elizabeth. You don't, that's true. Nobody sounds like that. When I shouldn't even admit to this, but I do this thing with my daughter where when she's being snippy and ignoring me, I speak for her just like that, but I do it in like a Mickey Mouse voice and she gets really mad at me. My daughter has a really high-pitched voice. I used to do the Munchkins from Wizard of Oz, and she eventually got so mad at me that she made me promise I wouldn't do that again, so then I switched to Mickey Mouse. As in like, oh, hey, Dad, yeah, I'll clean my room right away. Anyway. Yeah. I'm a bad parent, that's what I'm saying.
Or that's not supposed to be ally,
but yeah, like, totally fine. My advice would be develop the habit of, like, you're fine. So your math is good, you obviously understand what you're doing. I would say you want to kind of develop the habit of being a little bit more ordered in how you write things out, just for when you get to stuff. I mean, and we're not really talking about this, but when you get to stuff that's a bit trickier, it's good to have that as a habit. Yeah, you're great. Beautiful. Yeah, that's perfect. I'll say the same thing. Like, my advice, I have no advice. It's perfect. What you're doing is perfect. And then you're dividing by 100 at the end, right? Yep, that's fine. That's going to serve you great. And that makes sense to you, yeah? Beautiful. Do exactly that. What was I doing? Oh, I was showing that folder with Alfred. Off the top of their head, does anyone know what year I last taught grade 10 applied math? I'm going to guess 2018. Nope. Share. Alfred.
For a second there, I thought you were going to say a different word that starts with S.
Snappy? Yes. Yes. Sorbet. I like sorbet. Big fan.
yes, then
Why is the first thing in that folder a picture of Airbud? That's weird, right? This is my grade 10 math class. Oh, I know why. Culminating. The culminating was starting a pet store. I got it. I can call it right now. That's a pretty good culminating. I shall return. Howdy. Let's try it together, okay? Can we do that? Because I think now's a good time. All right, let's take a look. When we go to find the average atomic mass, what are we doing? The average atomic mass, in this case, I want the average atomic mass of what?
Iron.
How am I going to write that? Very good. All right, we're just going to take the sum of all the masses times all of the abundances. And when we put the abundance in, we're going to make sure we put them in as a decimal. All right, so let's do this. And I'm going to have to write pretty small. So let's take the first mass in abundance. What's the first mass in abundance? 53.9396. And I've got to multiply it by the abundance. And how do I write 5.85% as a decimal?
0.0585.
Beautiful. And if I didn't know that, what could I have done with this number? Just divide it by 100, because that's what percent means. Our second abundance is this one. So what am I going to do? Some sigma notation means between them. What do I put? Yeah, we're adding these together. And so what am I going to put here? What's our next mass in abundance?
55.9349 times 0.9175.
Nice. So this is the really common one, right? That's obviously the abundance we see the most of, right? Cool. What do I put before the next one? Sigma notation tells me that every time I am? Very good. Adding. What is my next abundance? Or my next mass in abundance? This one, right? And so what am I putting there?
56.9345 times 0.02.
Yeah, and remember, because this is a one-digit number, I got to make sure that zero's there. Again, if you weren't sure, I could have just taken that number and divided it by 100. Good. And then what's our last one? Oh, what should I do between them, of course? Add. If you're running out of space,
Just shrink it.
just shrink that. You bet. Look at that. I got tons of space. Don't tell me I'm running out. All right, what's that last one supposed to be? 57.9333 times, and we got to be careful with this one. How many zeros do we have to have for a zero-digit number? Dose, yeah, so 0.0028. And if we plug that into our calculator all at once, hopefully some of you already have the answer, but I will go here, 53.9396 times 0.0585 plus 55.9349 times 0.9175. So like this is cumbersome, but it's not hard, right? You're just plugging it in. Be careful not to switch any numbers. And again, I really want you to build that habit if you can of doing calculations all at once, because it helps us avoid mistakes. Because if you have to punch a number in twice, you know what I mean? Like calculate a number and then plug it back into your calculator, it's easy to make a mistake. So the fewer times you have to punch things into your calculator, the better off you are. Does that make sense? Now, just on the face of it, what's the really common isotope here?
56.
Yeah, so this number should be close to 56. So if I get 211, did I do something right?
No.
I may have done something right, but I did something wrong, right? So we press answer, and we get 55.845. Is that a good logical number? Is that close to 56? Yeah, I like that. So we'll say the average mass is 55.845. And what's the unit, of course? AMU. I should have put AMU on every mass in here. In fact, I'm going to just try and tell me I didn't.
You didn't
You
put
did
it
it.
on it, you put it under it.
I know, it's not great. It's not great. Questions about that?
Why is 54 and 56 stable but not 55?
Sorry?
Why is it that 54 and 56 are stable but not 55?
It's a complicated answer. The short answer is this. Why, if I say you had like a wheel bolt that had 8 lugs at certain angles to each other, it's stable, but if I took one of them out, it wouldn't be? It's just the arrangement. It just has to do with charge balance, with mass balance. There's gravitational effects. There's the strong nuclear force, the weak nuclear force, and then waveform equations. There's just a whole bunch of things that have to work together to make it stable. And most combinations don't work. No different than, if you imagine, say, a tripod, most of the combinations of leg lengths, like if you started playing with how long each of the legs were, most of them will result in it not being stable and tip over easily, right? Then there's a few different combinations that make it stable and hold in place. It's not a great analogy, but it kind of gives you the right idea. Was that useful at all?
Yeah.
I'll take it. That sounded like a pity, yeah, but I'm totally cool with that. Yes.
Why is the last yes lowercase while all the others are capitalized?
The last which?
Yeah, like in stable color.
Oh,
The practice.
I think probably what happened is when I pressed the space bar in each case, it auto-corrected to a capital Y. And then probably because that was the last one, I probably never pressed the space bar, and so it never auto-corrected. That would be my guess.
Wasn't a serious question.
Well, you got a serious answer. All right, listen. Your practice, you should not have any trouble with question 1 or question 2. Question 2, you are going to have to figure out the masses yourself. That's fine. You know how much a proton and a neutron weighs. Just know that you're not going to have a ton of decimal places to work with here. That's fine. Question 3 is a bit of a challenge. You're going to have to do some grade 10 math. Can you solve a linear system? Listen, look at me. If you can't get question 3, that's okay. Don't stress about it. I do want you to try. See if you can figure it out. But it's a bit of a challenge question. Does that make sense? So question 1 and 2 I want done. Question 3, I want you to try it. But if you can't get it, That's okay. Just like yesterday, I want you, when you've done your homework, if you've done it on paper, to snap a quick picture of it. At lunch today, I'm going to look through yesterday's work. Please make sure you have it in. Again, I'm not marking homework per se, but you're going to want to keep up with it, all right? It's important to keep up with it, not, look at me, I don't give busy work. I don't believe in busy work, I don't like it. If I'm asking you to practice something, it's because chemistry is a skill. There's two sides of it. There's the understanding side and the skill side. And the skill side, stuff like this, finding masses, stuff like yesterday, quickly knowing how many protons, neutrons, and electrons, it's not about being smart. It's just muscle memory. It's just if you do it a bunch, you'll do it naturally. There are things I remember from school that I don't even pretend to understand, but if I see it, I can just do it instantly because I've just done it so many times. That's the key to some of these things. Repetition. It's your friend. Have a wonderful day, guys. Be kind to one another. I will see all y'all tomorrow. I would spend a bit of time tonight working on that paper. All right? They're not due till Friday, but I wouldn't want to do it the night before. I don't know about you. I like to give myself a bit of time. Thank you. And of course, you can always message me if you have questions. If you have a computer, put them back. Make sure you plug them in. Or I'll
Break your knees.
break your knees. Ivan said it. All right. I was just going to say be upset with you, but cool. Ivan has set the standard, and it's knee breaking. I respect that. And if you have a calculator, please make sure it goes back nice and neatly. And yeah, what can I do for you, my
Are you
friend?
staying in here for a break?
I am.
Is it cool if I sit here?
Totally
and do the rest of the
cool.
homework?
Yeah, of course. Oh, you guys are adorable. Yeah, you're always more than welcome.
This is just a reminder that we do have sandwiches and a few snacks in the office if you forgot your
Where is
lunch.
my charging cord? Where did I? There's my phone. Oh, pardon me. Thanks, Toby. Have a great day.
Mr. Zamparo, please contact the office.